Start the recording.
You want me to start?
Oh
Okay.
no,
I,
Bruhat is.
Okay. Yes, starting. Okay, welcome everybody. It's a pleasure to have Ling-Yan Hung from Fudan University. I have known Ling-Yan for uh, more than a decade. So I've forgotten where from when but she in a sense she's my academic sister because we had the same PhD advisor in Cambridge. So from Cambridge, Ling-Yan went to do a postdoc in the Perimeter Institute, followed by another postdoc in Harvard, and then she moved to Fudan as faculty, and she's going to move to Beijing in February. So Ling-Yan, it's up to you now.
oh, thank you very much. So I would like to thank Aninda for giving me an opportunity to talk here again, and also to Pratik for making all the arrangements. So it's been some time since I last visited and gave a talk. So this piece of work is really a continuation of what I talked about back in 2019, and the hope is to continue. This efforts, trying to see how far tensor networks capture the essence of the ADS-CFT correspondence and capture uh, uh, dynamics of space and time in the tensor network. And so so what I'm going to talk about now has appeared on the archive work. It is work done in collaboration with my postdoc Chen Ling and my PhD student Xirong Liu. But the talk today would be focused mostly on the first two papers, and the last one, if there are other opportunities, I may. So the last one is very different in some sense. It has more technical stuff to do with p-adic CFT. But the first two papers, I hope it would look. The hope was that it would be, well. It still works only for p-adic CFT, but it's a fairly generic discussion the uh, of these tensor networks, and so we're going to see. So the plan of my talk is that I will start with a very brief introduction of the tensor network and ADS-CFT correspondence. In particular, I would give a lightning review of p-adic tensor network and p-adic CFT. Then I will talk about in the past, what I talked about last time in 2019 was that it was possible, we showed back then that it was possible to build a tensor network that plays the same role as some kind of pure ADS. So the next natural question is how to introduce curvature, how to push the tensor network away from that kind of pure ADS geometry. We got idea. We were inspired by how the usual ADS-CFT work, and we figured out a way to bend, so what we call bending the Bruhat-Tits tree, the counterpart of ADS space, that is dual to p-adic CFT. And this idea is basically to introduce some kind of RG flow in the p-adic CFT. By studying this RG flow, we figure there is some kind of discrete Einstein equation that is hidden there. Then we will end with some outlook and discussion. This is since there are not that many of us, so please feel free to stop me at any point to ask questions if anything is unclear. So let us start. Our hope, the holy grail of HKLL is to find a consistent theory of quantum gravity. So when we talk about quantum gravity, what do we mean by quantum? That probably means that we need to look for a set of algebra that describe we need to look for some set of algebra. And when we talk about gravity, we mean that there is some kind of geometry. So quantum gravity sort of, to me, means that you need to find a consistent set of algebra that where some geometrical data is hidden inside. That is certainly extremely hard. We know that if we apply canonical quantization to the metric, to Einstein theory, you do get some kind of algebra. Canonical quantization gives you an algebra of commutation relations between G and G dot, the conjugate momentum. But the problem is this program doesn't really work because it led to a theory that is non-renormalizable. It has and therefore it is not a consistent quantum theory. And the ADS-CFT promises a way to help us identify what that algebra is, because it says a CFT is dual to some gravitational theory or string theory in ADS space. So it would imply that the algebra that in the CFT is actually secretly telling us something about the gravitational theory, is the appropriate set of algebra for gravity. But indeed, that doesn't take us too far, because the precise map between CFT operators and gravity operators has not been worked out, and therefore knowing that they are dual to each other doesn't completely solve our problem. In some sense, the Ru-Takanagi formula is one very important breakthrough in this direction, because it tells us that the entanglement entropy of the CFT, the entanglement entropy of a CFT is a number that you extract from algebraic data of the CFT. And the Ru-Takanagi formula says it is related to the area of some minimal surface. So that tells us that some algebraic data in the CFT is related to geometrical data on the gravity side. So that is one important breakthrough in this direction, connecting appropriate algebra with geometrical data of the gravitational theory. And that inspired this tensor network program that says, in order to reproduce the Ru-Takanagi formula, it appears that the ADS space that encodes data of the CFT is perhaps some kind of tensor network in which the CFT degrees of freedom can be thought of as these dangling legs at the boundary of a tensor network, and a linear map is basically represented by this tensor network. So in case it is not completely clear what a tensor network is, let me just say two words what they are. So a tensor network is basically made up of tensors, and these tensors are represented graphically as these dots in a graph. And every vertex in this graph carries several legs, and these legs can be thought of as the indices of a given tensor. So a tensor network basically gives you tells you a way how these tensors are contracted with each other. If two vertices are connected by a line, then it means that these two tensors share a common index, and this index is summed over. So the original idea of the tensor network is that I can represent wave functions of the many-body wave function by rearranging it into a contraction of these tensors, and these boundary legs here corresponds to the original physical degrees of freedom. But depending on the nature of the problem, I might rearrange this boundary data into a network, and presumably the observation of the observation of Brian Swingle back in 2012, I believe, is that the ADS space behaved like this kind of mirror tensor network that is suitable for describing CFT ground states in which boundary degrees of freedom appears to be to represent a CFT ground state. It is most natural to consider okay, CFT ground states are sort of fixed point of coarse graining, and if I have a tensor network that looks like coarse graining in this extra direction, these are these entanglers, and these gray tensors are isometries that takes two legs to one leg. So you can see that this tensor network is a representation of real space coarse graining. And if I do it an infinite number of times, then it should generate something that is scale invariant. And so that would be a natural answer describing ground state of a CFT, which is also scale invariant. And it was observed by Brian that if I am interested in computing the entanglement entropy of the CFT, then it would correspond to looking for some minimal curve that cut through this tensor network in the bulk. And this picture would be very, very similar to the Bruhat-Tits formula, which says entanglement entropy is equals to the area of some minimal surface that cuts through the bulk with boundary anchored on the CFT degrees of freedom at the boundary of the ADS space. And so the tensor network appears to be appears to be capturing some essence of the ADS CFT correspondence. Put it differently, I like to say that ADS space is some kind of geometrization of entanglement data of the CFT. The tensor network is also a geometrization of the entanglement data of the CFT ground state. It turned the CFT, the entanglement data, into connectivity of these vertices in a graph. And so it turns entanglement data into geometry. And in that sense, the ADS CFT correspondence, at least the Bruhat-Tits formula and the tensor network, shares some similarity that doesn't appear to be completely trivial or superficial.
These two pictures, I mean, you started off by saying that the quantum gravity is algebra plus geometry, but these two pictures have not, do not seem to say anything about why gravity has to be quantized. Do they? I mean,
no, it doesn't say why gravity has to be quantized. It just directly, it doesn't, sorry, yes.
Yeah, so is there an answer to this question that can such arguments tell us why gravity must be quantized?
In the case of precise ADS CFT, then it must be in the original version of ADS CFT. Then
yeah, no, that's true. But then that's a circular argument, right? I mean, we actually. But I'm just wondering whether these kind of discrete ideas can tell us that we must be talking in terms of a quantum theory of gravity and not general relativity in some continuum limit. I mean, in the following sense. So, are there precise calculations where you must superpose different geometries to get a particular answer in the discrete theory?
Okay, I think yes. Okay. I don't know if the gravity degree of freedom would necessarily be would necessarily be dynamical, as in a separate degree of freedom from matter. As in the current example that I'm going to give, it certainly is not an independent degree of freedom. But on the other hand, if I say I construct a particular ground state by a tensor network, then I certainly can consider superposition of ground states in the CFT. That completely makes sense. If I do that,
so you have to talk in terms of superposition of geometries, as a superposition of different theories of gravity.
Right.
Okay.
But of course, that doesn't mean that the gravitational degrees of freedom is necessarily the metric that I'm directly quantizing the metric.
Yeah, no, but at least that's the first.
But it would still say that it is this. The whole thing is described by some Hilbert space that can be superposed.
Right.
Right, and in what I'm going to show in our example, gravity would not be an independent degree of freedom. What I am going to show has the flavor of low dimensional gravity. In fact, it has many similarities with 2+1 dimensional theories. And so the gravitational degree of freedom is actually not itself independent of the matter.
Okay, thanks.
Thanks. Okay, so so this tensor network picture was sort of interesting, but it hasn't been particularly useful in the sense that it is very difficult to make it very quantitative. So there are lots of nice pictures that people have presented, but as far as making very precise connection with Einstein theory or deriving Einstein equation, I think it is quite hard. So what in this slide, what do we mean by when we claim that we can derive or obtain Einstein equation out of such a tensor network? It would have several ingredients. So first of all, I have to say we have to decide what is the kind of graph that I would put a tensor network on. Then I would have to decide what are the tensors that I put on each of these vertex. And I have to optimize these tensors somehow so that it would represent my CFT, either the wave function of the CFT or the partition function of the CFT, but I have to know what numbers to put into these tensors. Once I have done that, I have to decide, because now I don't have any action or matter, I just have a bunch of numbers that I put into these tensors. So we have to figure how do we read off if there's some kind of matter that is effectively encoded by these tensors. And in the same way, we have to decide in what sense we are, or how do we decide the distance between two vertices on this tensor network. This distance certainly should depend on the values these tensors take, but it's by no means clear how do we assign distances to 2 points on this network. So assume that we managed to figure out what kind of matter is effectively encoded by this bunch of tensor, how to assign distances to these to 2 points in this graph. Then we can start computing some kind of curvature that is defined by the distances assigned to this graph. And maybe we'll be able to compute something that looks like a discretized version of the Einstein tensor. And if we have some idea of what the matter is like, then we can compute some kind of stress tensor in the bulk. And finally, we can compare this Einstein tensor and this stress tensor in the bulk and check if they are somehow related. And if they do, then we say, oh, Einstein equation is kind of encoded in this tensor network. And so that is one reason why it is super hard to get it, because there are too many guesses. And the graph, the tensors, what do we mean by distance? What is the actual matter that is encoded here? So by the time we finish guessing all of these things, nothing can be made precise, and everything at best is some kind of at best it has the right form, but it would be very, very hard to get something precise. And so that is why we started working with the p-adic ADS-CFT, because it is way simpler. And moreover, when we talk about discretizing ADS space, we break almost all the symmetries of ADS space. And when we want to work with precision ADS-CFT without any symmetries at all, without isometries, it's very hard to do anything concrete. And that was why we struggled for a while trying to work with discretized version of ADS space, and we realized that it's super, super hard. And that was one reason why we moved on to p-adic CFT, because in that case, several of the problems would be solved very naturally. What graph to use and what tensors to use as it will emerge. These two questions can be answered very easily, purely based on symmetries. And once these two things are done, then the rest seems to be more doable. So let me give a very quick review of what the p-adic CFT is. So for simplicity, let's consider working with a one-dimensional CFT. So our discussion can be generalized to any dimensions, but I think it is easiest to focus on one-dimensional CFT just because it's simpler. I don't want to get muddled by some technicalities when we move to high dimensions, but let me just say it is doable. And so in a CFT, we have space-time or spatial coordinates, and these spatial coordinates would be a real number. Under conformal transformation, in one dimension, it would be simply some kind of Mobius transformation. X goes to AX plus B over CX plus D, where ABCD forms a SL2R matrix. And under this conformal transformation, a primary operators would transform in this familiar way. And so a defining set of data of a CFT is that we need to know the spectrum of primary operators which are characterized by this conformal dimension delta I. And also we need to know the OP coefficients of when two primary operators move close to each other, they can fuse to, they can be expressed in terms of linear combinations of other operators. When the two of them are so close, they're indistinguishable. We can expand these two local operators as linear combinations of local operators. And so this expansion, OP expansion, is characterized by OP coefficients. So this is something familiar in usual CFT. What about p-adic CFT? The whole idea of the p-adic CFT is to replace real numbers of space-time coordinates by p-adic numbers. So we just replace the coordinates, space or time coordinates of the CFT by p-adic numbers. So what are p-adic numbers? As we know, real numbers, they are field extension of rational numbers. So all rational numbers are real numbers, but then as the folklore says, rational numbers, there are lots of holes in the number line, and to fill up those holes, they are completed into real numbers. P-adic numbers are basically other alternative ways of filling those holes and turn the rational number into a number field, so that multiplication, division can be. So all rational numbers are also p-adic numbers, and the p here corresponds to a prime integer. So every prime integer defines a different p-adic field, and so there are an infinite number. So it means that there's an infinite number of ways of completing the rational numbers into a field. And so every p-adic number can be expressed as a power series in P, treating P as a small number. Yeah, so this power series would not be convergent from the point of view of real numbers, but it is convergent from the point of p-adic number, because p-adic numbers have a notion of a norm of size of the number that is defined very differently from real numbers. In particular, if I write a p-adic number in this kind of power series, these AMs, they are integers that goes from 0 to p minus 1. So this power series is sort of like writing a number in base p. Except the digits grows towards the left. When we write a number, usually the digits start from the left and then goes towards the right. But the p-adic number, you can think of it as writing a number in base p, but the digits goes indefinitely towards the left. And AM are the digits that takes values from 0 to p minus 1, except for m equals 0, am cannot be 0. And so and in that case, if we make that restriction, then this leading power p to the v would be unique for every given such p-adic number. The p-adic norm of this series of this p-adic number.
Can I clarify a bit? So yes. AM, you said, can take on values from 0 to p minus 1.
Right.
And what is v?
V is an integer.
Okay, V is an integer, I see.
Right.
So what would
So
be an
it's
example
sort
of
of
a
like the
p-adic number?
leading power. Right.
Yeah. So what would be an example of a p-adic number if I mean, it's obviously something that is completely unfamiliar to us, but then can you give us an example of X?
Okay,
Which
yes. Let
yeah.
me give you an example. Let's
Yeah.
say, because every rational number is a p-adic number, so integers in itself are also p-adic number. So let me say 2. 2
Yeah.
is a p-adic number, but 2 is a 2-adic number. It's also a 3-adic number, a 5-adic number. So what does that mean? If I write 2 and I take QP, P equals 2, then X is equals to 2 to the 1, and that's it, right?
Mhm.
Then it says the 2-adic norm of 2 is 1/2 according to this line.
Mhm.
Now I can think of 2-adic number as a 2 as a 3-adic number, right? Now if I want to write 2 as a 3-adic number, then it would say that I have 3 to the power 0 times 2. 3 to the power 0, and then the rest of the digits are all 0. So then it means that the 3-adic norm of the number 2 is equals to 1, because the leading power p to the v would take 0 if I'm now working with 2 as a 3 expressed as a 3-adic number.
I see. And you said all real numbers are p-adic numbers, but irrational numbers like pi, they are not p-adic.
Right, they're not p-adic.
Is it known that they are not p-adic, or is it something that one
Right, it
says
is
that?
known that they are. It's known that they are not p-adic.
Okay.
You can see it here. The digits move towards the. It moves towards the left. This series is not ending to bigger and bigger powers of p. So most of the p-adic numbers expressed. So a generic p-adic number would be divergent if viewed from the point of view of a real number, and vice versa. So p-adic numbers, they are it's just a word of their own that exists because they have a different notion of big and small. And you see from the norm, the definition of norm here, it says p is treated as a small number.
Right. And when you say that the digits move towards the left, this is in the sense how we represent binary numbers. I mean, things in
Binary, let's say base 2 or base 3, normally we would have digits move to the right, in the sense that this p to the m would go down. I start with a leading power, let's say 100, then I start with 10 to the 2,
I see.
and then 10 to the 1.
Okay,
I
see. That's
specify the digits to smaller and smaller powers of 10.
Okay, thanks. Yes. Yeah.
Right.
That's okay. Yeah.
Right. So why did they introduce this weird definition of the norm? So somehow, because if I want to determine distance between 2 points, I can use the p-adic norm, and it would satisfy all the triangle inequalities. And so it would satisfy all the axioms satisfied by distance. Let's say 2 points are only two numbers are only the same if their distance is 0, and then it satisfies triangle inequality. And so it is a well-defined notion. It gives a well-defined notion of distances, and therefore it makes the this number field well-defined. Right. So so in practice, I spent some time talking about these p-adic norms. In practice, in the rest of the talk, we're not actually going to make much use of these properties. This is only a tool that gets us toward the bulk dual. But in case it would look too mysterious, so I spent a bit of time explaining what these p-adic numbers are. So in any event, p-adic numbers, once I accept that my space and time coordinates are p-adic numbers, then I can again define conformal transformation that are Mobius transformation, except now this ABCD falls into their p-adic numbers without normalizing these matrices. So I would say this matrix falls into the projective general linear group. So this is just for convenience that we put it as a projective general linear group rather than normalizing the determinant. And the so in a CFT, we would also need to define a set of primaries that transform in exactly this analogous way, except the norms are replaced by p-adic norms. And so each of these primary is still defined by a conformal dimension. And then once we have this primary, the next set of data is to define their OP coefficients, which are in exactly the same way. So what makes p-adic CFT simple is that you can see that different p-adic numbers, they have the same norms because it only depends on the leading power. So it means that smaller digits here, if you change the digits, it totally doesn't affect the p-adic norm of this number. What that means is that the derivative of these norms are identically zero. The usual notion of derivatives becomes identically zero. The norm is locally constant. And what it means is that when you look into a quantum field theory, that the field are real valued, but the p-adic, but the coordinates are p-adic valued, then the derivative of these p-adic fields would be identically zero. And what it means is that it would appear that there's no, you can't define the usual notion of descendants. And that is what makes p-adic CFT super simple. It would appear that all I need to care are the primaries and I can forget about descendants. It's actually not true that to say that p-adic conformal symmetry defined by this Mobius transformation has finite dimensional representations. They also have infinite dimensional representation, but the manifestation of the infinite dimensional representation is not visible in terms of by taking things close together. The descendants don't show up that way. And so at least it would appear very simple. Now, if I want to compute 2-point functions, 3-point functions, for example, then it takes exactly the same form as usual CFT, except we replace by, whenever we see a norm, we replace these norms by p-adic norms. Okay, so so that is so much about p-adic CFT. Then what about p-adic ADS? So the duality. So it was proposed that this p-adic CFT were defined, I think, back in the 80s, and these axioms that tells us all the algebraic data that defines a p-adic CFT, they were laid out by Meltzer, some guy back in the 80s. And more recently, I think at the end of 2016, Gupser, and unfortunately he passed away, I think, and that is a terrible, catastrophic blow to p-adic ADS CFT, because since then, I think hardly anyone or very few people works on it anymore. But in any event, in the end of 2016, he and his students, and also a separate group in Caltech, they are mathematicians mostly, proposed that if we have p-adic CFT as defined in the previous slide, then there should also be some geometric dual to the p-adic CFT. So how do we look for this geometric dual? They got inspired by the story of the usual ADS CFT. So let's say in one-dimensional CFT, the isometry group is SL2R, and the isotopy group, or the maximal compact subgroup, is SO2. Then what is ATS2 space that is supposedly dual to a one-dimensional CFT? The ATS2, you can also, which is conformally equivalent to the upper half plane. It is basically the quotient of SL2R, the isometry, by the isotopy group. So now we would like to repeat this story. These people repeated this story. And so what is the isometry group of p-adic CFT, one-dimensional p-adic CFT? That is PGL2QP. The isotopy group is PGL2ZP. ZP are so-called p-adic integers. And what they meant are p-adic numbers with norm less than or equal to 1. So, so it forms a subgroup. And if I now take the quotient, I also get a geometrical object. And very miraculously, this geometric object is discrete. And it looks like a tree, and it is the so-called Bruhat-Tits tree. And so these people propose that the geometric dual to p-adic CFT is basically field theory living on this tree. So what they okay, let me see. So let me say a few things about this tree. So in this tree, you have an asymptotic boundary, and you have something that looks like a radial direction. So you can think of this vertical direction as the radial direction, and this horizontal direction, and this vertical direction you can go off indefinitely. It's an infinite tree, and the horizontal direction, and asymptotically, the horizontal direction would form the p-adic line. So every vertex, the vertices would get more denser and denser as you move along the radial direction, and eventually it will become continuous. So the bulk is discrete, but the p-adic numbers themselves are continuous. And that you can think of them also as the p-adic line as living at the asymptotic boundary of this tree. So P is any prime number, and this tree is such that there are p plus 1 legs attached to each vertex if the boundary is QP. So every prime number defines a tree of p plus 1 valent. So what Gupser and friends did is that they applied the usual rule of ADS-CFT on this p-adic tree. They defined, so what they considered some scalar field that lives on this tree, and they computed the Green's function of this scalar field on this tree, and then they computed bulk boundary propagator of this scalar field, and then computed Witten diagrams defined on this tree. And so then they compared these Witten diagrams computed on using these scalar fields on this tree with correlation functions of the p-adic CFT, and they found that the functional form is in perfect agreement. And so they concluded that it seems that p-adic, there is some version of p-adic ADS-CFT correspondence. So what we did back in 2018 and 2019 was to see to what extent we can recover this ADS-CFT dictionary by considering a tensor network. So what we did then was that since the bulk is a discrete tree, it is very tempting to cover a tensor network on this tree. So without breaking any isometry, without breaking any conformal symmetry of the boundary CFT at all. Unlike the usual literature, which use a tensor network to reproduce the wave functions, we opted for reproducing directly a generating function of the CFT. And so in order to claim that we reproduce a generating function, I have to tell you what tensors I put in at every vertex and what boundary conditions I put on the asymptotic boundary, so that I would be able to generate all the correlation functions of the CFT. And we made
Janet,
some.
You said that the ADS2 equivalent was when you mod out by the subgroup which contains the p-adic integers. In this picture, what does it mean by modding out the subgroup which contains the p-adic integers?
Okay, so I haven't explained how the isometry group acts on these vertices. And so every vertex is labeled by a pair of numbers.
Okay.
So so you can see that I have a notion of depth, and so it is labeled by p to some n, and moving in the horizontal direction, I have to give it a p-adic number in the horizontal direction. And every such pair of numbers, I can form an upper triangular matrix that looks like, let me see if I can draw something. Is there a way to draw some sort of stuff?
On the PDF, probably not. Yeah. But maybe you can explain in words. Yeah. If it is too, if it is taking away from your talk, distracting you from your talk, you should continue.
Okay, let me just put it that way. I did not explain how the group acts, but then it roughly acts by there's a very specific way of how these PGL2QP matrices act on this vertex, and you just show one can show that the way this matrix acts keeps a vertex invariant when the matrix is restricted to PGL2ZP.
I see. Okay.
Oh, it is by definition invariant.
Okay.
Right. So okay. That is a bit technical. If you're interested, I
yeah, that's fine. Yeah.
Right. But yes. Right. I didn't explain how the isometry works, and therefore it sounds a bit mysterious. Okay. So I was talking about writing down. Sorry.
You can do full screen play. I think we are now seeing. Yeah.
Okay. And so I have to put down a tensor network that recovers the correlation function. So we made some very naive guess back then. Since every tree, so let's say focus on the case where p equals 2, then every this tree, every vertex would have 3 legs, and we needed to put in a tensor with exactly 3 indices on this vertex. So what kind of CHEP-th data is it at hand that we can put on that allows us to put here? And it seems that there isn't that many different choices, and a very natural choice would be to put in the fusion coefficients of the CHEP-th. It turns out that putting in the CHEP-th, putting in the fusion coefficients is not enough, and you have to weight every leg. So when 2 indices, so when an index is contracted, it has to be weighted by that index would be labeled by a conformal primary of the CHEP-th, and you have to weight that index when it is summed by p to the minus delta I, where delta is the conformal dimension of this index of this conformal primary corresponding to this index I. And so so we make this rule. If I have a p that is bigger than 2, then I would just make every vertex. So suppose p equals 3, then I would have 4 legs here, and I would and the rule is that I would take the tensor to be a fusion tree with 4 legs stuck into it. And then every leg would still be weighted by p to the minus delta. So in that way, I would be able to generate trees of arbitrary valency for any values of p. And then I have to specify boundary conditions in the asymptotic boundary of this tree. And I opted for the for putting if there's no operator insertion, then I will put this I'll project the boundary leg at the cutoff surface to the identity operator that I labeled 0 here. And on the other hand, if I have operator insertion at a particular point, then I would label that point. I'll project that boundary label to the specific operator label that I want to insert at the boundary. So in particular, suppose I want to insert 2 operators, one here and one here. And then I would project these 2 legs to O1 and O2 respectively, and all the other legs, they would be 0 or identity. Then you can see that these are fusion coefficients. So if I have O1 fused with 0, then I get O1. O1 fused with 0, I get O1, right? And so I would trace out a path of that is weighted by p to the minus delta I1, delta 1. And that this path, I collect powers of p to the minus delta 1 along this path. Every time I cross a vertex, I would collect p to the minus delta 1 because of the weights that I put into the tensor. And so what I would get for a 2-point function is basically I would get p to the minus delta d, where d is the distance of the path connecting these boundary points v1 and v2. So it just happens that this guy, p to the minus delta d, where d is the path distance on the tree separating 2 points, is a Green's function that satisfies a Klein-Gordon equation on this graph. And so the mass is related to this conformal dimension delta by this relation, where zeta p is some so-called zeta function that is defined in the following way. It's just some polynomials of p. And so the simple construction of our tensor network basically just reproduce naturally the fact that when I compute two-point function of the boundary CFT, the answer is exactly equals to p to the exactly equals to the Green's function that connects O1 and O2. The Green's function of some scalar field theory that lives in the bulk and with mass related to the conformal dimension by these relations. And this computation would be equivalent to what the ADS-CFT dictionary would tell us to do. And that was exactly what Gubser and friends did when they checked if the p-adic ADS dictionary would reproduce the correct CFT correlation functions. So in fact, you can start computing three-point functions O1, O2, O3. Then the answer this tensor network gives you with that it traces, it would pick up p to the minus delta along a path until these three paths finally meet. And so it would look like the answer is given by a Witten diagrams of bulk boundary propagator propagating from the boundary to the bulk until they meet at a certain point in the tensor network. And that is again what the ADS dictionary would tell us to do. But then it just emerged from this tensor network computation. And so and we can show that for arbitrary correlation functions at the boundary, you can basically this given tensor network would generate all the correct correlation functions of a given boundary CFT. As long as you know the fusion coefficients of this p-adic CFT, this tensor network would be able to reproduce all the correlation functions of the boundary CFT. Okay, so okay, I'm a bit slow, I'm sorry. I can't believe I spent so much time on talking about tensor networks that led to that we defined back in 2019, and by looking into this tensor network, at least we have some idea of what the bulk matter is encoded in this tensor network. And it seems that this bulk matter has a simple action, has a simple kinetic term, has a mass related to the conformal dimension of the CFT, and that the interaction vertex would be dictated by the fusion coefficients of the boundary CFT. And this, so far, this Green's function, you can see that I'm assuming that the distance of every single path here, of every single line edge that connects 2 points to be the same. And this Green's function already assumed that every single edge on the tree have the same distance. And so in some sense, we're working with a pure ADS geometry. The computation of the correlation function is as if we do not have to worry about back reaction of the scalar field onto the boundary. So we're working in a limit that is very close to a pure ADS. So then it would be, it's actually the core of what I wanted to talk about with only 10 minutes left. I'm sorry.
Janet, we started 5 minutes late, so you can take 15 minutes more. Don't worry about it. Yeah.
Okay. I try to be. I think 15 minutes. I probably should be able to convey the most important point. Sorry for being a bit slow.
You can take a few minutes extra. That's fine.
Okay. So so then we need to know how to bend the p-adic tree, and we were inspired by the usual ADS-CFT story where we introduce non-trivial boundary conditions. So remember, the original boundary condition is such that all the boundary legs are projected to the identity. And you can see that if most of the legs are projected to the identity, then you can see that 0 and 0, identity would fuse to identity. Identity fuse to identity. So identity operator is some kind, the identity label is a fixed point of this tensor network. It remains unchanged as you move down, as you fuse down this tree. If I want to introduce some non-trivial RG flow into this tree, I can imagine perturbing the boundary conditions from identity plus some other stuff. Then you can see that this tensor network begins to describe something that is clearly not pure ADS. So imagine you have some 0 plus j here, 0 plus j here. Then they would fuse to some 0 plus 2j plus j and j fused together. So it depends on the precise fusion rules, but it would be some complicated stuff here that is different from what you put in. And this complicated stuff and this other complicated stuff would fuse to some other things that gets even more complicated. And so you can see that the contribution to the partition function, once you change the boundary conditions, would flow. The contribution of the partition to the partition function from this tensor network is changing down different layers. And so it sounds like as soon as I move the boundary conditions to some other things that is not a fixed point under this tensor network, under the flow defined by this tensor network, the tensor network appears to be describing something that is no longer a pure ADS geometry. It is some complicated geometry. And so the question would be, how do we assign metric to this tree that has non-trivial boundary conditions? And moreover, we have discussed that there is some matter fields living in this tensor network. How do we read off expectation value of the scalar fields once you have non-trivial boundary conditions? Then if we're able to solve these two issues, then we would be able to identify if there is some kind of Einstein equation encoded by this tensor network. So this is the thing that I did with our postdoc and my student. So let's first discuss how to deal with expectation values. We have to define what it means by computing expectation value of bulk operators on this tensor network. And we made the following definition. The definition has to be such that it makes some sense. So how do we know it makes sense, and how do we define it? The idea is, if I want to insert an operator at a particular vertex, a bulk scalar operator, then I would stick an extra leg into this bulk, fuse an extra. So each of these legs are labeled by primaries. And remember, every vertex here is just a fusion tree. So in principle, I can fuse an extra leg into this fusion tree. And I define that this action of fusing an extra labeled A primary to this vertex as inserting a bulk operator at this vertex. So how do we see that these things make sense? Imagine I have my boundary is all identity. Then clearly, if I insert some A line here, then there's nowhere to absorb this A line. Because all the boundary are fixed to 0. And so this tree would have nowhere to absorb this A line. And so expectation value in pure ADS space would be identically equal to 0. Now, when the boundary is equals to a 0 plus j, assume that this deformation from the identity is small. Assume that this parameter j that we have defined here is a small perturbation, then we can compute the expectation value of a bulk field perturbatively in this j. Then the linear contribution would be some j here that source this A line. And so I would have a bulk boundary propagator, p to the minus delta d. D is the distance between this boundary point and this bulk point, and that would be bulk boundary propagator. And then I have to sum over the contribution from all the boundary points, and it would be given by this term. And then the set quadratic contribution would be 2 j's fused together and then sourcing this point. And so I would have bulk boundary propagator and a bulk to bulk propagator. And so these are results that are directly read off from the tensor network. But if you are for anyone familiar with the ADS-CFT dictionary, you would see that this expansion would be exactly what you expect if you introduce non-trivial boundary conditions for this scalar field, and the bulk expectation value would precisely take this kind of expansion that is based on bulk boundary propagators from the boundary to the bulk point. And so it looks like we have defined a way inspired by the usual ADS-CFT correspondence. We have defined a way of reading off expectation value of bulk fields. So then the next step is that, the few steps remaining is we have to assign distance to the edges. Once we have assigned distance to the edges, we have to assign curvatures to the graph. And we have been able to read off bulk expectation values to the bulk fields. Value of the scalar fields. In order to write down bulk stress tensor, we need to we have some notion of the bulk matter fields for reasons that we know how we have been able to identify the computation of correlation functions of the CFT with Witten diagrams by reading off what comes out of the tensor network. So the bulk contains bulk scalar fields. It has interaction terms, it has kinetic terms, it has mass terms. But remember, those computations were done where we're mostly in pure ADS or pure Bruhat-Tits tree. And now, in the presence of these non-trivial boundary conditions, the bulk is no longer a pure ADS. So we have to find a way to covariantize the bulk action. And then by varying with respect to how the bulk action is coupled to the background metric, then we would be able to define some notion of stress energy tensor. And once all these three steps are done, then we can check if the curvature is anyhow related to the stress tensor. But as I mentioned before, assigning distance to edges and assigning curvature is, and also covariantizing this bulk action for this discretized business is very hard. We don't exactly know how to do it. When we don't know how to do it, then instead of writing down something that is completely determined, we try to write down ansatz that are parameterized by many unknown coefficients. And we're going to work with a perturbative limit so to make things simpler. And by perturbative limit, I meant that these boundary perturbations are small. We work in a limit where we're very close to putting the conformal boundary condition, but we add a little bit of some other stuff at the boundary. So this J are considered small. Okay, so how do we write down distances? So let me show you this picture. When we want to, so the distance should depend on, so I'll be quick. So the distance should depend on the tensors. So if I want to assign distance to this edge between two vertices, then this distance should somehow depend on the tensors here and here. And so what exactly is the tensor data that is relevant on this edge? Recall how every vertex here takes the same values. So it doesn't mean anything if you directly ask what is the tensor value on this vertex and this vertex. They're always the same. But on the other hand, recall that when we have 0 plus j, I mentioned that 0 plus j and 0 plus j, they fuse to some other stuff. And this some other stuff fuse to some other fuse with this some other stuff with some more complicated stuff. So the RG flow, the essence of the RG flow is the fusion product at an edge, and therefore the distance should depend on the fusion product down this tree. So if I'm interested in the distance between these 2 points, then the data that is relevant would be the fusion product of all this stuff down up to this vertex. it would give me a vector, and this vector should determine my distance ultimately. But I have two vertices, so I can fuse from here all the way down to here. But I can also consider fusing all of this stuff all the way down to this part. So the relevant data defining distance here would be the fusion product up to here and the fusion product of all the other stuff up to here. And that is what I'm writing down here. V is the fusion product on one side of the edge, and V tilde is the fusion product from the other side of the edge. And because I'm working in the perturbative limit, it would appear like I start with the identity operator. If the boundary is exactly the identity, then every fusion product would give me identity. So I have identity plus some other small stuff. That is quite an arbitrary vector, depending on boundary condition. And similarly, V tilde should look like identity plus perturbatively some other stuff. And the distance should be a symmetric function of V and V tilde as a power series of this omega and omega tilde. And so we can write down a power series that requires only that it depends on, so J is the distance perturbed away from 1 for this given edge. So the distance is taken as d equals 1 plus j, and j is captures the small deviation from 1, and it is a power series in this omega and omega tilde. And all we require is that j depends symmetrically on v and v tilde. And so we expanded this thing up to cubic order in omega, and all of these coefficients are unknown. We don't know how to determine them, but at least we know that these things should satisfy certain symmetries. They should be symmetric in V and V tilde. Similarly, we want to define curvature on a given vertex, and so curvature around a patch, around a vertex, should depend on the distances of all the edges around this vertex. And moreover, it should be a symmetric function of all the of these edges connected to this vertex. And so we don't exactly know how to define it. Actually, the mathematics literature has defined a graph curvature, but we would pretend that we are not aware of that, and we will write down the most general power series expansion of the curvature of a certain point as a symmetric function of the distances surrounding this vertex. And so we can expand it up to quadratic order of this small distance perturbation. And these coefficients A0, A1, and B would be unknown coefficients. We don't know what they are. Then we will try to covariantize the matter action. We know that there's a kinetic term, but it should, and we mimic the usual covariantization and put in something that looks like square root G inverse. Well, square root G inverse in continuous theory, we know very well, square root G, we mimic it by basically just the edge distance. But square root G inverse, mu nu, the kinetic term is the counterpart of d mu phi g mu nu inverse, right? If we don't know exactly, but on a discrete graph, we don't exactly know what is the counterpart of g mu nu inverse. And so we will assume that the kinetic term, when covariantized, would depend on the edge distance on this edge connecting vertex xy to some power k, and we will allow k to be arbitrary. Then we also have the cubic interaction terms. HABC should be proportional to the fusion coefficients, but the dependence on but how it couples to the edge distance, we would allow it to be some arbitrary function that again has a power series expansion in this J. When J equals 0, H should be just 1, and HABC should be just these fusion coefficients. But when for arbitrary J, that I would expect that there's some J that shows up as a power series in the covariantized action. So I've introduced lots and lots of unknown coefficients. I don't know what they are, but I impose some very basic symmetries of these numbers based on what locality and symmetry of the graph. Okay, so so once I parameterize this assignment of distance, assignment of curvature, and assignment of the covariant matter action, I can use this data to write down. I can use this data to vary with respect to J, and write down an Einstein tensor based on what I call curvature that defines Einstein-Hilbert term, and I can define a stress tensor that came from varying with respect to my proposed covariant action. And so, and once I obtain the covariant action, I can replace the scalar field by the expectation value on the tensor network. And similarly, the Einstein tensor would be expressed in terms of this J. And once I have got this J, I can replace it by this expansion that again came from data of the tensor network. So what I would get is some very complicated things that depends on data on the tensor network, or the Einstein tensor would look like some very complicated data on the tensor network. The stress tensor would also, the bulk stress tensor also looks like some complicated power series on the data of the tensor network that came from replacing this expectation value of the stress tensor using the tensor network data. Now we'll ask the following question. Is it possible that Gxy is somehow equals to Txy? So this is a very complicated function of this expansion of the that tensor network data. So in general, that if I impose that Gxy and Txy are equal, then I have actually an infinite number of equations of constraints that constrains Gxy, that constrains the coefficients that I put in as the ansatz of the expansion of the distance and the curvature and the definition of the covariantized action. It would be a lot of an infinite number of constraints on these ansatz. So does there exist even one solution of these ansatz such that Gxy plus Txy can be equal to 0? That is the question that we ask. If Einstein equation is possible, is actually encoded in this tensor network, then maybe there is at least one solution of these ansatz. And the answer is there is indeed one solution to this ansatz, and it is exactly 1 up to overall normalization. So we impose that G plus T is 0, and so every coefficients of every independent terms following from every independent term of this boundary, that tensor network data, we would get some constraints on the coefficients that we put in, this unknown coefficients, and it gives and up to overall normalization, it gives one result, and the result was quite interesting. It says that if you put things back in, it would say that up to linear order, the Einstein tensor that we got is actually equals to some graph, some box of this edge distance. And if you compare with the mathematics literature, you'll find that they are actually in agreement. That is exactly the definition. If you expand the graph curvature that Yao and company has defined, you'll find that the curvature that we got happens to be the same, at least up to linear order, up to overall normalization. That came from requiring that G plus T is equals to 0. And moreover, these are, and the mass has to satisfy the relationship between the mass and the conformal dimension has to satisfy this relation that we impose. That is imposed. That is the same as in the usual ADS-CHEP-th dictionary. So this basically falls out of requiring that G plus T equals 0, and it says the Einstein term has to be this. And moreover, when the dust settles, we can ask what exactly is this distance between 2 points, an edge on the tensor network. It turns out that it has a very simple interpretation as a Fisher information metric. People like Tadashi and friends, they have attempted to interpret distances as some kind of Fisher information metric on this C mirror. And here, by requiring that an Einstein equation is satisfied at all, it tells us that the distances that is defined here can be rewritten as a Fisher information metric, which is related to the overlap between two very simple states. And these states here, actually, what is this quantum state here? I'm going to end in 1 minute. This quantum state here is actually defined by sticking so the boundary conditions are all determined. If I stick an extra leg on this vertex, I would be defined. I would have a tensor network with exactly one dangling leg. And so in that sense, I have defined a wave function with one index, right? And the distances that we defined turns out to be the Fisher information metric between two states, where each state is defined by sticking one leg at the vertex x and y. So if you stick a vertex, stick a leg at vertex x, you get a wave function. Then you stick a vertex at y, you get another wave function. That overlap gives the distance between these 2 points. That is what that is what imposing the Einstein equation would lead to. It says the distance is just this kind of Fisher information metric. So let me conclude. So we worked with a toy model of a CFT where the tensor network where there exists some tensor network that can recover all the correlation functions of the CFT, and we find that if we impose that an Einstein equation exists, or we ask the question, can an Einstein equation be encoded, a local Einstein equation, can it be encoded in this tensor network? We find that for the most general answers, that exactly one solution up to normalization is possible. And that answer would automatically give you that the Einstein tensor looks like what is defined in the mathematics literature, at least up to linear order in perturbation around constant curvature. And of course, this is nowhere near to what real CFTs are like, but more recently, we're working with we're trying to generalize this picture to real two-dimensional CFTs using some techniques of these Levin-Wan models that are topological that would help us to grow a bulk. But this is totally beyond the scope of this talk. So let me just end here. I'm sorry for exceeding the time limit. Thank you.
Thanks very much, Janet. This is a very interesting talk. I have a couple of questions. So maybe others can, if others have questions, they can start first, and then I can ask mine.
Yeah, I have 2 questions.
Yes.
So one is this pushing these operators to the tensor networks is similar to this Harlow Praskilians. They did this for the happy codes or something, right? So in that sense, how do you incorporate black holes or something in your tensor network?
Oh, this is a brilliant question. So first of all, it is not exactly the same. It is not exactly the same, as a Harlow Praskil kind of tensor network, in the sense that we are not using unitaries or isometries in this tensor network, because in general the fusion coefficients are not isometries, but that was necessary at least in the current context to reproduce the correct correlation functions. If you put in unitary stuff, then the correlation functions would not look like power law. So we were forced into using this kind of non-unitaries, non-isometries to reproduce the correct correlation functions. But on the other hand, it is similar to what they have in the sense that isometries and unitaries have the property that they are invertible in all directions. If you separate the legs into two groups, then the tensors are invertible. In that sense, this tensor network is also invertible to some extent, and therefore in that regard it is similar. So about black holes, So in this case, we are helped by symmetries to construct black holes. In the case of okay, in the case of a ADS3, BTC black holes are quotients of pure ADS3 space. By quotient by a subgroup of a conformal group, then you would be able to generate an orbifold, and the orbifold, an orbifold of ADS3 space actually gives you a BTC black hole. In our case, in the p-adic black hole, in the case of this p-adic CHEP-th, a similar story works. You can basically do an orbifold on the BT tree, Bruhat-Tits tree, then you will be able to generate high genus curves. And those high genus curves would be the counterpart of BTC black hole. And so in that regard, we could generate the analog of BTC black holes. And that it was in this paper, this third paper, we try to extract the temperature and the and the entropy of those black holes by doing orbifolds on these curves, orbifold on these trees, and generate black holes.
So pictorially, can I think that you just remove some tensors and put some black holes in that place?
As orbifolds, it means that let's say, let me look at the tree. So look at the isometries of this tree. So if I have an infinite tree, then I can, so imagine that the asymptotic boundary is all the way at infinity. So I can translate these branches along, so this brown branch, I can translate these branches along this branch, right? So that is an isometry of this tree. So one of the ways of generating a BTC like black hole is to consider identifying up to several steps of translation on this brown on one of these branches. And if I do an identification orbifolding by translation along this branch, then you can see that the resultant geometry looks like a circle. This brown branch would be compactified because I start to, let's say, identify this point with this point. If I identify these 2 points, then I would generate a circle with 2 links, and then these other branches would be sticking out like a sun, the rays of a sun from a circle. And so it would look like this brown branch after orbifolding will play the role of some kind of horizon in a Euclidean black hole, and then these other branches would continue off to infinity from this horizon that is formed by this brown branch. So that is roughly how it works. You can also generate wormholes, high genus surfaces by considering several branches and then do orbifold on them separately. So that was a prescription that mathematicians gave in writing down high genus curves based on orbifolding this tree.
So okay, thanks. So another question is that if we think in terms of this holographic kind of renormalization, you separate out some regions of your bulk and similarly some separate regions of your boundary. I mean just so in that sense, how does this work in this bulk picture actually? I mean,
you mean separate out?
Not separate out. I mean, you just integrate out some region of your boundary, and that is equivalent to integrating out some region in the bulk, right? In the normal or usual ADS safety dictionary.
Let me see. So I understood it as let me see how to how to say this. So in the usual okay, I guess. Right. So what happens usually is that we turn on some boundary operator, right? And then we say that we can find an effective cutoff surface in the interior, and that corresponds to having integrated out some parts of the boundary away, and I find a new effective theory in a new cutoff surface, and that has different couplings.
So the radial direction is your p prime numbers.
Right, p to m, p. So the radial direction is parameterized by p to some power, and the power increases towards the boundary. So when we say RG flow, we meant that if I start with a boundary conditions, after going to one next level, the boundary conditions has changed. It has flowed to some other boundary conditions.
Okay.
So because these boundary conditions would correspond to couplings of relevant operators that we have turned on. So it tells us that when you turn this on, when J is non-zero, after one some fusion, which you can consider as coarse graining of the boundary theory, when you reach this second blue level from the purple level, then the couplings have moved to different values and it has flowed.
In this picture, this bulk is not like mirror tensor network, but is this BT tree.
Mirror tensor network is not. It's very similar in that if we look at the mirror tensor network, it's also lots of bulk legs, and then it is a constraint to fewer and fewer legs towards the bulk. So in that regard, it is very similar. What is different is that this BT tree doesn't contain this kind of disentanglers, and so it doesn't contain any loops in the in the network. It is a tree tensor network. Generically, tree tensor network, if you use tree tensor network to represent real CFT ground states, it would produce terrible results. As in, if you consider computing the entanglement entropy, it would totally not recover the right entanglement entropy of a real CFT. But on the other hand, for the p-adic CFT, the correlation, the notion of distance has changed. And so it just happens that it happens for the case of p-adic CFT that a tree tensor network actually covers the correct entanglement structure of the CFT. But the difference between mirror and this tree is that mirror contains loops in the network, and this tree is a tree. It doesn't contain loops, and that the isometry of the conformal symmetry is an exact isometry of this tree. Whereas in the mirror tensor network, the ADS symmetry, the ADS isometry is broken terribly, and so it's hard to tell what exactly is the isometry that is left in the mirror tensor network.
Janet, let me ask you my question. So, in the description that you gave, I did not see a role that large n or maybe the ADS radius, ratio of ADS radius to string length that would play. So, my expectation would be that you will get an equation like G mu nu equal to T mu nu only when this R divided by string length is much bigger than 1. So where did that information or where did that intuition go? And so when you actually say G mu nu, could it be that you're actually, because of the fact that ADS has a lot of symmetry, you're actually not being able to identify curvature, higher curvature terms which have symmetrized indices from G mu nu, the Einstein tensor?
Okay, this is a great question. So the quick answer is I don't know why it doesn't require any large n limits, because in the case of this p-adic CFT, because there is no clear, so people hope to define some notions of descendants, but they haven't yet been able to come up with a way to understand this. But the usual notion of stress tensor and descendant of the boundary CHEP-th is not there because they don't have descendants, and therefore they don't really have the notion of a central charge. There might be some counterpart, but we don't know what it is, so therefore, first of all, we don't know what is central charge, and on the other hand, so we don't know why. In some sense, it works too well. Maybe one shouldn't expect it to work too well, but nonetheless, it seems that.
Yeah. So there was an expansion that you were doing in your equations where you actually truncated to j cubed or something.
Right. So, we were working in the limit where the deformation. So if all the boundary conditions are set to projection to the identity operator, to the identity label, then that is a fixed point of this tensor network flow. Because 0, 0 fuse to 0, 0, 0 fuse to 0. So it would fuse to 0 at every vertex, and therefore every vertex would contribute equally to the final value of this partition function. And so all the edges would have the same length when the boundary is mostly all 0. Now, when we change the boundary conditions from 0 to 0 plus a little bit of something else, then the distances would be very close to being equal. Let's call that 1. Let's normalize that to 1 when everything is 0. And if I put in some other thing, then every edges would be expected to have the distance 1 plus a little bit of other things. And we were expanding. And this we were expanding in this deformation from having all the edges being 1. So J is the small deformation of.
So implicitly, there is no scale in that deformation. Just wondering.
True. It's just that it is already a dimensionless number.
Ah, I see.
So the ADS scale is sort of like 1, and this deformation is small, is a dimensionless number, small compared to 1.
Right, and maybe that is what we are supposed to identify as lambda prime or whatever. I mean, the ratio of the, yeah. I mean, there is, when you say that the deformation is small, it's small with respect to what? So
it's small with respect to because every this edge can be normalized to have distance 1. So I can say this edge distance is d over L. L is ADS scale.
Right. And yeah, okay.
Right, and the deformation is small compared to d over L.
I see.
So
okay.
I guess, okay, I could think of maybe ADS scale is the only distance scale, and these small deformations are also measured in the ADS scale.
Yeah, okay. So that does not give you alpha prime, of course. I mean, you require another scale, which tells you
right,
that.
Right.
Yeah, okay. I see. Interesting, because I would have thought that the more discretized your geometry is, the more stringy it will be. But it seems like here, if what you're saying is correct, then that is not true. I mean, this is a counterexample to that intuition.
Okay, that I understand what you are saying, because there is some objections by, I think, Carroll and friends. They wrote a paper saying that you can't get sub-ADS sub-ADS locality is lost if you discretize it, and you wouldn't be if you put in a very regular mirror tensor network, then you wouldn't be able to see sub-ADS scale, right? And in this case, it seems that we didn't have to worry about that, and the reason was because the usual notion of descendants are not there.
Okay. Yes.
And therefore, it doesn't require sub-ADS locality. And indeed, there's no sub-ADS. In this case, there's no sub-ADS locality.
I see. Okay. Very interesting.
Right. So in that sense, this game, I don't know to what extent one could continue playing to give useful things. But on the other hand, we are also sometimes fascinated by, let's say, some results of one of Gupta's students. Let's say they had some identities derived from the p-adic ADS of those conformal blocks. I don't know if you saw some of these things, and even though they obtained it from the p-adic ADS CFT, that somehow it works on real CFTs.
I see.
And so it might be, there might be some very magical fishy, I don't know, thing that and also this guy he and Yao wrote a paper saying that, let's say if I put string theory where the string worldsheet is this p-adic tree. So the upper half plane open string, I replace the open string worldsheet by this tree, which is the counter. It's a discretized, sort of a discretized version of the upper half plane. And they want to write down the beta function, like in the usual string theory case, write down the beta function and set the beta function to 0. So the target space of this worldsheet is still real space-time, and the string, but then the worldsheet itself is this discretized tree, and then now do the usual string theory thing and write down the beta function on the worldsheet. And that beta function is still Einstein equation of the target space.
I see. Okay, so this is like the string bit version of the string worldsheet, I suppose.
Yes.
Yeah. Okay. I see.
But of course, that is not related to this tensor network business. And to be fair, I don't know to what extent this toy CFT and toy ADS can tell us about the real version of ADS CFT, but I was still somewhat surprised that a unique Einstein equation seems to come off from this network.
Interesting, I see. Okay, very nice. Thanks very much for patiently explaining your work to us. It was very interesting. I think we can stop recording, and then hopefully we will meet up in regular times, whatever regular means actually.
I don't know.
Yeah.